So hello, welcome to day 2 of chapter 4. I don't know why I'm doing things with my hands. Yeah, welcome to the next bit. Today I'm going to get through the second third of chapter 4. Once again, chapter 4 is a long one. So I'm going to lecture on Friday also, do practice problems on Monday instead. But it was all about forces. We introduced so far Newton's laws, 1, 2, and 3, but the big one being Newton's second law, F equals ma. And with that, talked about free body diagrams. That's important. We're going to go into that. Really though, the last thing I talked about was a special force called the normal force that says that if you have an object sitting on the ground, there is a normal force. It is the force holding it up. Right here, no normal force. It's hanging. It's only when you're sitting. And I'm going to basically pick up with the next important special force, which was actually why I just grabbed this. Tension is another important problem. Tension is the force exerted by a rope or a string. If I wanted to do a free body diagram for this situation right here, I would say that gravity is downwards and the tension is what holds it up. The tension is straight up because, yeah, that's what's keeping it up. Likewise, if you pull something across a flat surface, it's tension that pulls. Anytime you have a rope or string, that is tension. Now, an interesting thing about tension is it's always the same everywhere in a string. What that means is if I do this, and while I pull this side to side, it goes up and down on my finger, the tension on the vertical part and the tension on the horizontal part will be exactly the same. That tension is not changed by pulleys. It's just, well, the direction would be different, obviously. Oh, this is about to get much more awkward. My cat just decided to come and help play with us. The direction will be different, and we'll worry about this guy in a second. Sorry, I have a cat walking in front. But if I go like this, I can say the tension holding the string here is the same as the tension in the string there. That tension is the same everywhere, just in different directions. Now, tension is important enough, it also will get its own symbol. Tension will be represented by the letter capital T. You could also use F since it is a force, but normally gets its own T. I'm going to do a simple problem, and then I'm going to make this shit complicated. Because we've yet to do that. I said before, this is the hardest chapter, so I might as well make it hard at some point. So, let's say an elevator is fully loaded at 10,000 kilograms. What's the tension in the cable when it pulls up the elevator with an acceleration of 5 meters per second squared? Well, if I want to find, oh dear God, if I want to find the, sorry, she's like starting to push that stuff off. If I want to find the tension in that cable, I have to start with my free body diagram and my F equals ma. Now, F equals ma is really two equations, one in x, one in y. But if I look at this, nothing's going on horizontally. It's all up and down. So I'm only going to look at y. And then I'll go and make my free body diagram, which actually shouldn't have showed up already. Should be showing up now. My timing thing is off. But this is my free body diagram. I have two forces acting on this elevator. Gravity pulls it downwards because there's always gravity, and tension is what holds it up. And so I'll say T is up, mg is down. Now, when you're doing your forces in y, your forces in y equation, I've said before that in this equation, F equals ma, the most complicated part of this equation is this guy. That will always be in its own little equation. And for y, it will always be forces up minus forces down. So I look at this picture and say T goes up, mg goes down. So this would be T minus mg equals ma. I dropped the a sub y here. I just made it a because it's the only acceleration. And there it is. There's my equation. T minus mg equals ma. That equation isn't always true. It just happens to be true in this case because of our free body diagram. If I want to solve for the tension, I can add mg to both sides. I factored out the m just to make math easier. And I can plug in and solve. And that'll be the tension. Any questions though? Oh, that's all right. I want to do a more complicated problem with tension. But before I do, I'm going to introduce one other idea, and then I'll do a more complicated problem. And that's the idea of equilibrium. Equilibrium means the sum of forces equals 0. Anytime you say something's in equilibrium, that means it's either velocity of 0. Well, okay, equilibrium means acceleration is 0. That's what equilibrium means. It means the sum of forces is 0. If the sum of forces is 0, acceleration is 0. That could be something's moving with a constant velocity or not moving. And if anytime something's not moving or moving with constant velocity, we can call it equilibrium. And equilibrium problems are kind of more the simple version of force problems, because instead of F equals ma, it'll just be F equals 0. And in any equilibrium problem, you just say the acceleration is 0. Okay. So let's do another force problem with tensions, but this one in equilibrium. And the problem is this thing I keep grabbing and putting in front. I'm going to do it again. It's this right here. This right here is meant to be a scene from the end of Iron Man 3. At the very end of Iron Man 3, it's kind of spoilers, but it's an old movie. I don't care. At the very end of Iron Man 3, the president of America, and here I'll put this behind for a second, is suspended by 2 cables. And I have the 2 cables here, one going this way, one going this way. And he's hung by 2 cables while in the Iron Patriot suit. The cables holding the president are at angles shown below. One's 53 degrees, one's 33 degrees. What is the tension T1 and T2 in the individual cables? Given that the president's mass in the suit is 318 kilograms. Yes, I bought this little action figure just to do this problem. Now, if I want to solve this, I can say, okay, I got, let's see, this would be to the left to me, so it's to the right to you guys. So I have my T2 and my T1. And when I look at this, I can say those are my forces up. Also, because he's on Earth, I have gravity going down. And so what I'll do is I'll start with my free body diagram. And I'll say what forces are acting on Iron Man or on the Iron Patriot. And I'll look at this and say, I have my T1. There's a rope here. It's pulling on it. That rope pulling on it, that's going to be one of my forces. So this right here is T1. I have my T2, which is right here. There's another rope pulling this way. If I have another rope pulling that way, that's my T2. Tensions are some of the easiest forces to make on a free body diagram because they're normally pretty visible. I got a big string hanging and pulling this way. That's a tension. And the last force acting on my little guy here will be gravity, where gravity will be mg because gravity is always mg. And that'll be my free body diagram. You see, he hangs because of all of these. If I remove one of them, like if I remove T1, he's going to go woo and go sliding off. It's all of these forces together that puts him in this position. Now, if we look at this, we can say this is equilibrium. We know it's equilibrium because he isn't moving. He's staying stationary. He has a little bit of rocking going on, but he's staying pretty stationary. And so I say, okay, we got a free body diagram. We know F equals ma, but because he isn't moving, and if you want to know where that was in the text, I say he's at rest. Because he isn't moving, I can say my acceleration is 0. That circle kind of missed. Now, I could try to do this with vector addition. I got all these vectors. I got my T1, I got my T2, I got my mg, but it's going to be a real pain in the ass. And this is how we're going to treat most force problems like this. I'm going to move this out from in front of me first. Actually, no, I can work behind this guy. See, what we're going to do, I'll just move my mouse out, is what we're going to do is we're going to say, if we want to go and solve for T1 and T2, what I'm going to do is look at this and say, you know what? I like to work in a standard coordinate system. I like my X and my Y. I don't want anything at an angle. In T1, it's up at an angle. T2, it's up at an angle. Neither one is straight along X or straight along Y. And anytime I have any vector that isn't straight along X or straight along Y, I'm going to fix that. What I'm going to do is I'm going to say each of these vectors, T1 and T2, they will each have an x component. I'll have a T1x and a T2x. Well, T1x will be T1 cosine of 53. T2x would be T2 cosine 33. I know that because my angle is measured from the horizontal. And as long as your angle is measured from the horizontal, we can say this one's better. We can say the x component is just the magnitude cosine of the angle. And so this little x component right here, that would be T1 cosine of the angle. I can also find my y components. My y components, which would be this right here, I could say my y components would be T1 sine theta 1 and T2 sine theta 2 respectively. That my x components are cosine, my y component is sine, unless you're measuring from the vertical. We're going to come back to that later today. Now this free body diagram is kind of complicated. I mean, this was our free body diagram. But if you ever have a free body diagram like this, where the angles aren't, vectors aren't straight along x or straight along y, break it into components and redraw it. See, I can say this is the same as this. That T1 is T1x plus T1y. T2 is T2x plus T2y. And I'm going to take these vectors and I'm going to split them in half and say that is really my free body diagram. This guy isn't being pulled up at an angle. He's simultaneously being pulled straight this way and straight this way. That's what I'm doing. I'm saying this is the same as if there was two other strings. You know what? Fine, be that way. This would be the same as there was two strings instead. This one string. And it would be as if it was one coming out, one going up. Likewise, I'm doing the same with the other side. I'm breaking it down to two vectors, one in the horizontal, one in the vertical. And since the sum of forces is 0, that means that my sum of forces in x is 0 and the sum of forces in y are 0. Okay. Any questions so far? Because that was the hard part. Actually, that's not true. The hard part is still coming, but the hard part is algebra. But we're going to worry about that in a second. Okay. So let's use these equations. Sum of forces in x is 0, sum of forces in y is 0. My equations in x are always right minus left. Let's see if one of you guys can do it. Is anyone willing to unmute themselves and say what my equation in x is going to be? Take that as a no. In x will be right minus left. So what I'm going to do is I'm going to look at my picture and say, to the right, I have T2x. To the left, I have T1x. And so my equation in x is T2x minus T1x. Or T2 cosine 33 minus T1 cosine 53. Now I can add T1 cosine 53 to both sides and divide both sides by the cosine 33, but I can't solve for T2 without T1. So that's as far as I can go there. Let's look at my equation in y. So let's try this again. Can someone watching tell me what the equation in y is going to be?
T1 sub y plus T sub 2y equals mg.
I would have phrased it slightly differently, but that is true. I would just do it as a minus. T1y plus T2y minus mg equals 0, which is the same thing as what you said. You just added mg to both sides already. But yes, up minus down. Everything up minus everything down. Up is T1y, T2y, down is mg. Which is the same as T1 sine 53 plus T2 sine 33 minus mg equals 0. This leaves you with two equations with two unknowns. Anytime you have two equations with two unknowns, how to solve is you're going to substitute one in for the other. I'm going to take this T2 and shove it in down there for T2. And I'm going to say it's T1 sine 53 plus T2, where this is T2 sine of 33 minus mg. Now at this point, I got to make some space. So any questions before I do that? Okay. So this equation on the left has only T1 in it. There's no T2 left in it. So I will add mg to both sides. And then I'll factor out a T1. On the left side of my equal side, both terms have a T1, so it can be factored out. I can then divide both sides by everything in parentheses and plug in and solve and solve and solve. And so I know T1, the magnitude of this vector right here, must be 2620 newtons. And did I lose anyone? We good so far? We didn't lose PB apparently. She's just sitting here watching. Let's get T2. To get T2, T2 equals T1 cosine 53 or cosine 33. That's what was my X equation gave me. I'm just going to shove in my T1 and solve. And that's my values. Questions? Okay. If there's no questions, let's do another one. This one says, a woman at an airport, remember when we used to go places? A woman at an airport is towing her 18-kilogram suitcase at constant speed of 2 meters per second by pulling on a strap at an angle of theta above the horizontal. She pulls on the strap with 360 newtons force, and the wheels have a resistor force opposing the movement of 15 newtons. What angle does the strap make with the horizontal? And what's the normal force? So, if I'm going to solve this, let's make it a little smaller. If I'm going to solve this, I start all force problems the same way, a free body diagram. I have to say what forces are acting on that suitcase. Now, I'm going to try to do this again like how I would normally do it in person, but involves some audience participation. So, from anyone listening, what are the forces acting on this suitcase?
15 newtons to the left. I don't know if that's how you're negative 15 newtons, and then 36 newtons at theta.
Give me with names.
So we have R equals 15, negative 15. Is that what you want?
I meant, okay, the 15, that would be a friction force. So it says a resistive movement. So, yep, we have a resistive force to the left. I got that one. What else? What was the other one you said?
We have her pulling it of 36. So
Yep, we have her pulling it. What else? There's more
gravity.
forces. Gravity.
And then in the normal force.
And then the normal force. Those are my forces. And I say, there we go. There's my forces. There's my free body diagram. I also say she's moving at a constant 2 meters per second, but it's constant. We don't give a shit what the value of V is. That is useless information there just to throw you off. I've put a problem like this on the exam before, and people always put that number in for A. But that's not an acceleration. That's a velocity of constant. We don't care. All we care about that it's a constant. It means A equals 0. That number there, that 2 meters per second, is just there to mess us up. So we'll get rid of it. And I can look at my free body diagram and say, okay, if that's my free body diagram, I can now try to make my equations with this. But if I want to make my equations with this, that T is up at an angle. That T is going to be a pain in the ass. So we need to split it into components. And since it's up and to the right, I'll say it's two different vectors. One that is up, one that's to the right. We'll have my Tx and my Ty respectively. Tx being T cosine theta, Ty being T sine theta. Now that I have my free body diagram, now I can try to solve. Because I know F equals ma. But since I said constant velocity, that means zero acceleration. That means this is equilibrium again. And once again, this really is two equations. This is the sum of forces in x equals 0, the sum of forces in y equals 0. But that is going to come from my picture. So I can look at my picture and find my equation in x and my equation in y. So let's see if I can get someone else this time. But if not, I'll have the same person. What's my equation in x going to be?
Tx minus f.
Yep. It's to the right to the minus the left. Tx minus f. I wrote t cosine theta instead of t of x just because I already put that in. But yep, you're exactly correct. How about in y?
N plus ty minus mg.
Yep, exactly. And oh wow, there's cat hair everywhere. She's shedding like crazy. It's n plus ty minus mg. And we can solve for things. Now, it doesn't matter which equation I do first. I used my x equation first because if you go back to the problem, I asked what is the angle and what is n. And I want to solve for this angle, which is the same as this angle, and n. My y equation has two unknowns. My x equation has only one unknown. So let's deal with my x equation first with only one unknown. This is what makes these problems complicated. The problems from this chapter have a lot of algebra, and there's going to be no set process follows. Like projectile motion, plug into this equation, solve for t, plug into the other one. This is going to be rearranged to get whatever the hell you want after you make a free body diagram. And I'll say for x, I know that t cosine theta minus the resistor force is 0. I can add the resistor force to both sides, divide both sides by t, and take the inverse cosine. And by plugging in some numbers, I can get the angle. This angle has to be at 65.4 degrees. At any other angle, she'd have acceleration, be it positive or negative. Any questions though? I also asked what is the normal force. If I want to solve for the normal force, anytime you want to find the normal force, use your y equation. I can look at my y equation, say n plus t sine theta minus mg equals 0. If I take that equation and add mg to both sides, and then subtract t sine theta from both sides, I can get the normal force. The normal force is m times g minus t sine theta. That'll give me a value. So any questions? Seriously, if you're lost, let me know now, because I'm about to make this much more complicated. And if you're lost now, when I make it more complicated, it's only going to be worse. Okay. Let's say I got something just sitting on a flat ground. And if this car is just sitting here, I can say, okay, sum of forces. There's nothing in x, so let's ignore x. And in y, n is up, mg is down, n equals mg. Nice and simple, right? But let's say instead of having a car just sitting on a flat ground, let's say instead I put on a ramp. When I put the car on a ramp, it accelerates downwards rapidly and repetitively with the video looping. That the second I let go, sorry, that's really funny that my dot cam is just my cat's full. That second I let go, it's just going to accelerate down this ramp. I don't know why it's not moving forward when I try to go forward. And you can see all these green dots, that's acceleration. So let's look at what it looks like on the ramp. You see, when I just go and put it on the ramp, what I can do is I can say, well, gravity is straight down. Gravity is straight down because gravity is always straight down. Boop. But the normal force is not always straight up. The normal force is whatever direction perpendicular to the ramp. And so here the normal force is up and at this angle. For my car, it's up at a steeper angle. If I hit play on this, I think I lift it to a higher angle. That as I go higher and higher and higher, what I'm doing is I'm shifting the normal force to be at a, nope, to be at a steeper and steeper angle as I lift it. And that as I lift this, I'm just going to slowly bring my normal force to a larger angle till eventually it slides. And so what I can do is I can say, okay, there's my forces. Now, if a standard coordinate system, I would say my mg is straight along y, or negative y at least. And my n is somewhere between x and y. So you think, let's break n into components. But when I let this go, when I just set this going down, all of the acceleration is down the ramp. None of the acceleration is in the same direction as normal. It's all with it. And for this reason, because when something goes down a ramp, its motion goes with the ramp, it is easier to tilt our coordinate system. That instead of doing the standard x is to the right, oh, that was stupid. Okay. Instead of doing the standard x is to the right, y is to the up, I'll say x is along the ramp and y is perpendicular to the ramp. And by doing that, I say my normal force is in the positive y. And all of my acceleration is just in the x. That by putting this tilted coordinate system, I say x is that way. All of the acceleration is x. I can say ax equals whatever the hell it is. Ay is 0. There's no acceleration in y. Acceleration in y would mean as it's sliding down the ramp, it suddenly jumps up off the ramp or falls down into it. But there's a problem with this. If I do this, that means gravity is no longer on the y. That gravity is in between x and negative y. And my gravity needs to be split into components. Now, there's a trig identity that I'm not going to define. I'm just going to tell you as a fact that says this angle right here is the same as the angle of the ramp. And I can use SOHCAHTOA to break mg into components. And I can say the x and y component of mg. But if when you look at what the angle I said, this angle, this angle right here, that is from the vertical. And I kept saying the x component is cosine, the y component is sine, as long as it's from the vertical. Ramps will always be backwards. On a ramp, you will always want to use a tilted coordinate system. And you will always want to break gravity into components. And for everything else, x component cosine, y component sine. But for ramps, gravity will be backwards. On a ramp, x is sine, y is cosine. For all the ramps, mg sine theta, mg cosine theta. You're going to need to do this. And that's how you set it up. And this will let you make your force equations. In y, I'll have up minus down. If it's not going off the ramp, aka if it's not going up like this or down like that, but it's going with the ramp, aka that. Oh, pause. I can say my acceleration y is 0, and it usually will be. So my forces in y is n minus mg cosine theta. In x, I only have one force in x. X is right minus left, but there's nothing to the left. My only force there is mg sine theta. So it's mg sine theta equals ma, or g sine theta equals a. Then I have an acceleration down the ramp, which we saw repeatedly. And I have an acceleration down the ramp because gravity is pulling it down it. Questions though? Let's do an example problem. My example problem is about a man named Sisyphus. In Greek mythology, Sisyphus was punished for chronic deceitfulness by being told that he had to roll a boulder up in Hades. And whenever it got to the top, it rolled back down. and he would forever repeat this action. Let's take Sisyphus here and replace the boulder with a frictionless block. And assume the gravity of Hades is the same as the gravity of Earth, because sure. What force does one need to exert to push a 100-kilogram boulder up a 50-degree incline at constant velocity? And just for fun, Part B, what's the normal force? I picked 50 degrees because that's about the picture of this angle of this picture right here. So let's say, want to solve for force required to push it up, constant velocity, normal force. If I want to solve this, it's a force problem. I'm going to start this the way I start all force problems, free body diagram. Now, it is a ramp. Because it's a ramp, I'm going to tilt my coordinate system. I'm going to put X up the ramp and Y perpendicular to the ramp. I have to sneeze and it's not coming. There we go. That scared the cat. It's her fault I'm sneezing anyways because it's cat hair everywhere. So, if he's pushing this boulder up the ramp, what forces are acting on this boulder? See if one of you guys can answer. So anyone, what forces are acting on it?
So the normal force is going in the y direction.
Uh-huh.
Gravity is going straight down. And then he is pushing it at an angle parallel to the incline.
Exactly. Yep. Gravity straight down. He's pushing it up. I call that F sub S for force of Sisyphus, and the normal force is in the Y. So I say, cool. There's my free body diagram. But if I'm going to do a tilted coordinate system, and easy, like often when I'm doing these problems, like I literally just take a piece of paper and like and look at it tilted. If I'm going to do this, I'll just tilt my head instead. I'll say, okay, N is straight up. Cool. F of S is straight to the right. Cool. MG is at some component. MG needs to be split up. And I got to break gravity into its X and Y components. And using SOHCAHTOA and the logic I just said last slide, I'll break it into mg cosine theta and mg sine theta, where cosine will be the Y component and sine will be the X component. And this gives me my free body diagram. Now I said he's moving at constant velocity, so his acceleration is 0. And really this is two equations, one in X and one in Y. And I'll just make an equation for each. My X equation is right minus left. And so I'll say, okay, we got, oh, that's what I wanted. I wanted this. I'll say right minus left. So it's F of S minus mg sine theta. My Y equation is up minus down. So it'll be N minus mg cosine theta. And I can solve for things. I asked for the force of Sisyphus. That's F of S. I'll just take my X equation and add mg sine theta to both sides. Plug in some values. Solve. I also asked for the normal force. I'll take my Y equation and add mg cosine theta to both sides. Plug in some values. Solve. Any questions? Okay. I'm a little worried I might be going a little fast today because I'm a little bit further than I should have been. So I do apologize. But if no one's saying anything, I don't know when I'm going too fast. Please let me know if I go too fast.
Professor, I would let you explain one more time in this example why you switched the Y and the X.
Because, let me go back a tiny bit. Because, clear this angle here is the same as this angle there. And so I'm not measuring from the horizontal, I'm measuring from the vertical. And how I got the sine cosine was SOHCAHTOA. SOHCAHTOA says sine of the angle is opposite over hypotenuse. And so this right here, that's opposite. So that is the sine. Cosine of the angle is adjacent over hypotenuse. This is adjacent, so that's the cosine. Does that make sense?
It does. I'm just nervous that I won't see it. So maybe just some more practice problems will help.
You'll get plenty with the chapter 4 homework, and I'll give some other problems. Just with ramps, you just always put the cosine sign backwards. But yeah, we'll give you practice problems, don't worry.
Okay.
Which, oh, when I'm done today, I'll talk about some things on practice problems. I've been giving out practice problems like crazy to a bunch of high schoolers, actually. So I have some more resources I can give you guys too. So, last topic I want to get into today is what happens when you start tying shit together. Let's pull this back over. Actually, I'm not going to pull the whole thing over, just this. Let's say I take this side and tie it to my arrow here. And you're in a pulley. If I let go of this, what's going to happen is that the arrow is going to go to the right and the weight goes down, right? Well, if they're tied together, they're going to have the same acceleration. That whatever the arrow's acceleration is will be the same as whatever the weight's acceleration is. Anytime you connect objects, the magnitude of the acceleration will be the same. Also, the tension will be the same. The tension this arrow feels and the tension this weight feels will be identical because it's the same string. A pulley does not change that. And so if I say that there's like 5 newtons of force in this horizontal piece, that means there's 5 newtons of force down in this vertical piece. The thing is, though, is sometimes the direction of the accelerations change. If I was to solve the problem shown before you here, I would say that the blue block has an acceleration in x. I would say the orange sphere has an acceleration in negative y. But the magnitudes would be the same. The magnitude of the acceleration in x would equal the magnitude of the acceleration in y for the other one, because they're tied together. When you have things tied together, watch your accelerations. Watch what direction they're in. But really, for the most part, magnitudes would be the same. I'm going to do a kind of simple problem with this that is not what I wrote, so it's boring. Oops, just click with the highlighter. And here's what I got. There's a truck. It has a mass of 8,500 kilograms. It pulls a trailer. It has a mass of 27,000 kilograms. There's a draw ball attaching.
Yo.
I'm failing here. There is a draw ball attaching the truck to the trailer. If the truck accelerates at a rate of 0.78 meters per second squared due to the motor exerting a force D on the truck, what is the value of the tension between the truck and the trailer? And what's the value of D to accelerate at that rate? So that's what I got. I have one force I already gave. This force D, that's just from the truck's engine. And the truck is pulling this trailer, and there's a tension in the thing between. If I want to solve this, well, I'll start with a free body diagram. And I'll say if the truck is accelerating at 0.78 meters per second squared, the trailer must be accelerating at 0.78 meters per second squared. If the trailer was accelerating slower, you'd be leaving it behind. If the trailer is accelerating faster, that'd be really bad because that means it's going faster than you, it's rear-ending you. And I can look at this and say what forces are acting on each. You see on the trailer, I would say there's gravity, there's a normal force, and it's being pulled by this tension T. This drive force D that we started with doesn't touch the trailer. The only thing affecting the trailer is that it's being pulled. Meanwhile, the truck has gravity and a normal force, but the truck has a trailer dragging back behind it, and the engine is pushing it forward. And we know that the tension on the trailer equals the tension on the truck. And so even though the truck's engine is revved up, it's making it go, that doesn't really affect the trailer. It affects the tension in between. But the engine is not on the trailer. You don't add the engine to the trailer. You only keep it with the truck. But if you want to solve for stuff, F equals ma, we make our equations. I'm only going to work in X. There's nothing important coming out of Y today. Normal force equals mg is all I'm going to get. And I would say I can make an equation for the trailer and the truck. To start with the trailer, I would say an X for the trailer. There's only one thing in X in the trailer. It's the tension. It's the only force, F equals ma. The tension equals ma. Except I have to use m2a because I'm doing the trailer, so I use the trailer's mass. I asked for two things, though. I asked for the tension in that draw bar, and I asked for the force the engine of the truck is doing to propel it forward. So let's look at the free body diagram of the truck. On the truck, still can ignore y, and we can say my equation in X will be right minus left. To the right, I have D. To the left, I have T. So it would be D minus T equals ma. But now I'm going to use M1A. The trailer isn't part of it anymore. You see, they were set up to the same, but once I set them up, I'm like, we're looking at the truck. That's the truck. That trailer is something else over there. We don't need to worry about it. If I want to solve for D, I'll simply add T to both sides. Plug in my numbers and solve. Any questions though? Okay. That is everything about forces except friction. Friday is going to be all friction. Keep in mind a week from Friday, not this Friday, but next Friday, March 5th, will be your first exam. You have covered everything on problems 1, 2, and 3. Problem 1 will be free fall. Problem 2 will be projectile motion. Problem 3 will be forces without friction. And 4 will be forces with friction. I would do friction on Friday. Probably
Wait,
a good.
That's
what was that?
that's like pretty much like the exam that we're gonna have. Those are the stuff that it's gonna be on.
Yeah, exactly.
Oh, okay.
The beginning of this lecture, the day 1 of these lecture notes, I do that a little slower and have it actually written out if you want to see it. It's in the PowerPoint or the video.
Oh,
So, sorry, what was that?
I was saying, oh, okay, like gotcha.
Okay, cool. I recommend looking at last semester's exam. I will solve it Wednesday of next week. If you want more practice problems, I've had a request from someone else who's not in this class, who's a friend of mine whose kid is taking physics elsewhere, asked for some stuff to help her daughter. And I sent her a link today, and because I sent it to her, I was thinking about it, so I should mention it to you guys. I published SUNY OER, so like basically completely free online textbook of just problems that'll have nerd base, like superheroes and such things, movies, D&D, that type of stuff, like the type of stuff I ask problems about. I published a whole booklet of them that's online. If everyone wants extra example problems, shoot me an email and I'll give you that link. Or just Google like OER Schweidenbach, you should find it. But just so you know, I can give more problems if people want them. But other than that, I'm going to stop there. I hope everyone has a good day, and I'll see you Friday. You have homework on chapter 3 due tonight, and you have lab due tomorrow. Have a good day, and see you later.
What time's the study hall?
Time's what?
Like I'm in the study hall, like
Office hours?
like office hours, yeah.
Office hours. Today I had office hours earlier, and I have more from 3 to 4:50.
All right, gotcha.
My full list of office hours is on Vanco Hall, but that's what I have today.
All right, thanks.
No problem. See you.